Hello everyone, today we are going to talk about balls. Really. So a ball in topology is defined, an open ball, by the way. An open ball in topology is defined as a set of points y, where y is in some set q, such that the distance between x and y is less than some number r, where r is between 0 and infinity. Now, we already see that the open ball set is a metric space, since it is equipped with a metric on it. So it does not make sense to talk about balls on sets without a metric being defined. Now, this definition may seem a bit foreign, but let's motivate it. So if I have some point x, and x has some radius r, and a radius just traces out a circle, right? Now a ball set is a set of points y, where y is in some set q, such that the distance between x and y is less than r. So let's say I have some point q here. We see intuitively that the distance between x and q is less than r, right? If you were to stack up q next to r, it's less than the magnitude. Now, if I have some point j, we see that j is not in the ball set, since the distance between x and j is greater than r. And if we had some point omega that lies on the endpoint of r, we see that the distance between x and omega equals r. So it's not less than r, so it's not in the ball set. So we see intuitively that everything inside this yellow circle, called the boundary, is in the ball set, since the distance between x and any one of those points will be less than the distance between will be less than r. But however, the boundary itself is not included in the ball set, since any point along the boundary, the distance between x and that point will be equal to r, and the open ball set only includes points that are less than r when the metric of x and y is applied. So in other words, this just forms a ball without the boundary. So you have all the points inside this boundary is in the ball set, but not the boundary itself. And that's why it's called an open ball. So that's the motivation for this definition over here. Now let's actually give some applied examples of balls. Some more concrete examples. Here is an example of a ball on R2. Now the metric of R2 that we are using is defined as the square root of x squared minus y squared. So let's just make this big X and big Y, where big X is defined as x2 minus x1, and big Y is defined as y2 minus y1. Okay? So an open ball on R2 would just be equal to a set of points, well, we should really change it. Set of points, say omega, or omega is in R2, where the distance between omega and the distance between that works. Distance between x and omega. Let's make it big X, really. The distance between x and omega is less than r. Now I'm using omega instead, since we already have a y here, so I don't want to throw us off. So we're using omega instead. Okay. So let's actually draw R2. we have the y-axis, and we have the x-axis. So we have some point x here. X might be, yeah, x is like x1, y1, right? So it's a set of, and there is some radius from the elements x in the set. And this radius, of course, forms a circle, since the radius goes in all directions. So the balls are the set of points omega, where the distance between x and omega is less than r. So that just includes all the points within this boundary. And that's why it's called an open ball. It actually looks like a ball, but without the boundary. It's open, kind of. Now note that everything outside of this is not in the ball. And also note that we can actually choose any value of r that we want. We can have the ball of x1 where r equals 1. You have the ball of x2 where r equals 2. Where r equals 2. So this ball may be this ball may be for r equals 1, but for r equals 2, the ball doubles in size, and intuitively, when r equals 1/2, the ball shrinks in size by a factor of 2. Okay? Now I want to give an even more explicit example of a ball, an open ball on the R line. So the open balls on the R line, it's just a set of points y, where y is in R, such that the distance between x and y is less than r. And here the metric dxy is just y minus x, the magnitude of that, absolute value of that. Okay, so let's actually draw the R number line. Here I have 0, here I have 1, here I have 2, here I have 3, minus 1, minus 2, minus 3. Now, I want to give a bit more explicit example of a ball. So let's choose the ball where x equals 0 and the radius is 1. So what does this ball look like? Well, here I have x is 0, so let's just put a point right there. Put a point at x equals 0. And the radius is 1. So the distance between x equals 0 and any other point y, where y is in R, it has to be less than 1. So, of course, 1 cannot be in the ball set, nor can minus 1 be in the ball set. Since the distance between 0 and 1 is just 1, and the distance between 0 and minus 1 is just 1, and the distance between 0 and y has to be less than 1 for y to be in the ball set. So we see that we see that all the points that are greater than minus 1 but less than 1 will actually be in our ball set, since the distance between x equals 0 and any one of those points will be less than the distance between 0 and minus 1. And that's just an open line segment, right? So in other words, the ball set of x equals 0 and r equals 1 would just be the set of points y, where y is between minus 1 and 1. So this doesn't actually look like the normal ball we know, but it's still a ball, right? It's just open balls on the real number line are open line segments. Now I want to give a proof about balls. I want to prove that the null set can never be a ball, can never be an open ball. When I say ball, I really mean open ball. So here's the proof. We start with the definition of an open ball. Then we say that R has to be between 0 and infinity. Then note that if the distance between x and y equals 0, it implies that x equals y from one of our postulates of the metric. Note that x equals x, that's just the identity property of elements, and this means that and note that 0 will always be less than r, and this proves that the null set can never be a ball, or which means that an open ball can never be empty, pretty much. So how does this actually prove it? Well, here's the this is a formal proof, or sort of formal proof. Here's the actual reasoning behind it, because we have x equals x, right? So the distance between x and itself will always be 0, right? And 0 will always be less than r, since r has to be greater than 0 by definition. So the null set can never be a ball, since there will always be a point that is less than r, that being x, since the distance between x and itself will be less than r. So it will always be in the ball set, since the ball set constitutes of points where the distance between x and y is less than r. So, in other words, the ball set will always, the open ball set will always include x, these center points, even if there is nothing in the boundary except x. X will always be in the ball set. You can have a ball set with the radius of 1,000. The center point x will always be in the open ball set. Okay. Now I wanted to find something called a closed ball. You probably guessed it, but a closed ball is defined set of points y, where y is in q, where the distance between x and y is less than or equal to r. So this is just an open ball, except that the boundary is closed. It includes the boundary as well, and all the points along the boundary, the distance between x and that point will be equal to r. I also want to define something called a sphere in topology. Now this isn't the normal sphere that we all know and love. This is a bit different. A sphere set is defined as a set of points y, or where y is in q, such that the distance between x and y equals r. So this actually only includes the boundary. Nothing inside, nothing outside, just the boundary itself. So a sphere on R3 would just be the geometrical sphere that we usually speak of, except that it only includes the surface. So it only includes the surface. So spheres in topology, they only include the outer boundary by definition. You have to intuitively demonstrate that the union of an open ball. Yeah. Also, probably should have mentioned this earlier, but a closed ball is noted with a tilde on the symbol. So a closed ball is just the symbol for an open ball, but we have a tilde on it, and this here uses an S. So we can prove that the union of a closed ball with an open ball and a sphere will actually just be a closed ball. You can take this as a definition for a closed ball, or you can take this or you can prove this yourself intuitively. This makes sense, right? Since an open ball is just everything inside the boundary except the boundary, but a sphere is the boundary itself. So now we have everything inside the boundary, and the boundary, which is just a closed ball. So you can prove this a bit more rigorously, but that's the intuitive demonstration as to why the union of an open ball and a sphere is a closed ball. So if you're wondering, balls have a wide range of uses in topology. For example, the standard topology on the real on R2 is actually the set of open balls. Standard topology on R is also the set of open balls. I think topology on Rn is just a set of open balls as well. Balls are also useful to define neighborhoods and other things. Yeah, balls are really useful in topology. Also, in my next video, I'll be talking about the L infinity space. So stay tuned for that one. Thanks for watching. Please share it if you found it useful. And yeah, have an amazing